Now we go on to talk about eigenspaces. We've been talking about eigenvalues and eigenvectors. This is the fourth video in that sequence, starting from 31, where we talked about eigen concepts. 32, we talked about computing eigenvalues and eigenvectors. In 33, we talked about diagonalization of matrices, which is something totally relying on eigenvalues and eigenvectors. So here we talk about eigenspaces, and we'll see how that bears some kind of resemblance with spaces, talking about vector spaces, which we had considered previously. So uh, explains this lesson explains systematically with definitions. This lesson explains eigenspaces rather systematically with definitions, theory, and worked examples. So, introduction. In linear algebra, eigenspaces describe the directions in which linear transformations acts by simple scaling, right? So they help us understand how matrices transform space, diagonalize matrices, solve differential equations, analyze systems in engineering and science. To understand eigenspaces, we first need eigenvalues and eigenvectors as usual. So you can't talk about eigenspaces because it is a space for eigen concepts. So by way of review, we've seen this amply that talking about eigenvalues and eigenvectors. Let A be an n by n matrix. A non-zero vector V is an eigenvector of A if AV is equal to lambda V. We've seen that quite well, where lambda is an eigenvalue. So here we see that if a matrix A acts on a vector V, then the effect it produces is to scale the vector itself. It doesn't change, it can change the direction of the vector, but it doesn't knock it out of its of its line, so to speak. So it scales it, it can shrink or expand it, and then reverse the direction, but then it remains on the same place. So by way of interpretation, when A is applied to V, oh, okay, I mean, it's the same thing I've been talking about. The direction does not change. The vector is only stretched or shrunk, right? So eigenvectors represent invariant directions. They are fixed vectors like that. And then we go ahead to talk about definition of eigenspace. So let A be an eigenvalue of A. I mean, let lambda rather be an eigenvalue of A. So the eigenspace corresponding to lambda is actually E sub lambda, which is the collection of all vectors in the n-dimensional system such that AV is equal to lambda V. So it contains all eigenvectors for lambda and the zero vector. So all eigenvectors for lambda and the zero vector. So we have the null space form, which helps us there. So the eigenspace can also be written as E lambda, which is the null space of A minus lambda I. We've talked about null space the other time where we saw that it spans all the possible values, all the possibilities where in the sense of matrices, right, where we had AX equals 0, right? So eigenspace is the null space of A minus lambda I. So eigenspace is the null space of A minus lambda I. Now, why eigenspaces are subspaces now? So if, for instance, if we have that A minus lambda I multiplied by V equals 0, so by taking the determinant of A minus lambda I, we get eigenvalues. By solving for V, we get eigenvectors, right? So we see that this is a homogeneous system because it's equal to 0. Therefore, we say that E sub lambda contains the zero vector clearly, and it is closed under addition. It is closed under scalar multiplication. So E sub lambda is a subspace of Rn because it obeys all the necessary conditions for subspaces. Now, the question now is how do you find an eigenspace? So here we're looking at a procedure for looking for eigenspace. So the first thing we want to do is to find an eigenspace. Step one, find eigenvalues. Usual thing we do. So find the absolute value, the determinant rather of A minus lambda I equals 0. Then next, form the matrix. To form matrix, you compute A minus lambda I. Then number three, you solve the system. So solve system A minus lambda I for X equals 0, solve for X, that is, then write solution, express the general solution as a span. So let's look at a very good example with a very simple, straightforward matrix. Now, find the eigenspaces of A, which is 2, 1, 1, 2. Step one, eigenvalue. Determinant of AI is absolute value of 2 minus lambda, 1, 1, 2 minus lambda. So you find the determinant, 2 minus lambda times 2 minus lambda minus 1 times 1, that's 1. So if you put it all together, you have lambda square 4 minus 2, 4, we have 2 times 2, 4. Uh, okay, 2 squared, that's 4, right? Then 2 times 2 times lambda, that's minus 4 lambda. Then plus lambda squared. So this is lambda squared here. That 4 is minus 4 minus 1, you have 3. So you can factorize that, you have lambda minus 3, lambda minus 1. So the two eigenvalues are lambda 1 is 3, lambda 2 is 1. I mean, we've done that a couple of times. So the next thing is you want to now find eigenspace for lambda equals 3. So that'll make you, so that's more like looking for, so that'll help you get the eigenvectors, right? So for eigenvectors, if you can come back here, so since you have 3, just say 2 minus 3, that's minus 1. Then you have this one, 2 minus 1, 2 minus 3 is also another minus 1. So it's more like you're looking for eigenvectors, right? So it's more like eigenvectors, but then you are expressing it as in terms of span after getting eigenvectors. So to solve a minus 3ix equals 0 now, so it means that so you now have, so it's more like you have minus 1 1 1 minus 1 multiplied by xy, right? So okay, I guess I want to do that. Minus 1 1 1 minus 1. Okay, minus 1 1 1 minus 1. So you have minus 1 1 1 minus 1. And you're looking for, so this is more like you're looking for this. This is the x, that thick x now is actually a vector representing xy, and this is 0 0 like this. So and then you can, of course, we want to expand this out, right? So what you need to do is check the rows, two rows, then you write the columns twice because you have two rows. So write this twice. So you have xy xy. So then you have minus 1 1 1 minus 1. All this now will be 0 each. So that means you have minus x plus y equals 0. That's on one hand. On the other hand, you have x minus y. X minus y equals 0 also. So altogether, it simply tells you that x is equal to y or y is equal to x. Same, same. So that simply means that if you have x, y, so when x is 1, y is also 1. Basically, that's what that tells us right there. So you have 1, 1 as the eigenvectors there. So all you just now need to do is, so the eigenspace for lambda equals 3 is E3, which spans 1, 1. That's all. So just write it as a span of 1, 1. And that is the eigenspace for lambda. So just like you get eigenvector corresponding to each eigenvalue, so eigenspace is just like that, except that you now write that span of that eigenvector. So in a way, you can say that an eigenspace is the span of an eigenvector. That's all. So for eigenspace for lambda, lambda equals 1 now. So you do the same thing. So by the time you do that kind of thing, x plus y is 0. That means x is equal to minus y. So if x is 1, then y is minus 1. So then the eigenspace for lambda equals 1, E1 is actually the span of 1 minus 1. So it's to find eigenspace, just find the eigenvalues, find the eigenvectors. So the eigenspace is a span of the eigenvector. That's basically the idea here. So now you want to compute, so we have a 3 by 3 matrix now, and I mean you can easily read off the eigenvalues. You have 2 2 2 here as the eigenvalues even without trying too much. So then you have that. So you want to compute a minus 2y, that be 0 1 0 0 0 1 0 0 0 like that. Then you can, if you solve the system, okay, this one has been done in such a way that it looks like I have to do it by all means. But let's see. 2100 21002. Okay. 210 210021. So let's say A is 210021 002. Okay. That's what that matrix looks like. So I'll skip as much as I can skip since we've done this amply previously. So 210021 002. Okay, I mean, from here, I don't have to waste time with the determinants, right? With the eigenvalues, okay? So this is what we have now. So I don't have to waste time because this is it. Since it is a triangular matrix, I can easily read off the eigenvalues. So we know that for here, the so we know that lambda is equal to 2, and that happens thrice. So we have the eigenvalue is 2 with a multiplicity of 3, basically. So in that case now we can so it means we are going to get just one eigenspace. So to find the eigenspace now, to find the eigenspace, of course, the only eigenspace we have here is E2, because all the lambdas are the same, E2 all the way. So we just need to find eigenvalues. First, find eigenvectors, not eigenvalues. Find eigenvalue. So first, find eigenvectors. And how do we find eigenvectors? Just come here and say that you are looking for uh, a a minus lambda I v is equal to 0. So what is a now? 210, like that. So we have 210, 0, 2, 1, 0, 0, 2. Okay. Minus lambda into 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. Okay. And v is v1, v2, v3. Okay, and that is 0, 0, 0, like this. So, and then we have 2, 1, 0, 0, 2, 1, 0, 0, 2, minus lambda 0, 0, 0, lambda 0, 0, 0, lambda into v1, v2, v3 equals 0, 0, 0, like this. So we tidy all this up. We have 2 minus lambda, 1, 0, 0, 2 minus 0, 2 minus lambda, 1 minus 0, that's 1. Then 0, 0, 2 minus lambda into v1, v2, v3. Okay, we already have our lambda, right? Okay. Okay. Lambda is 2 now, so this is 2i here. So this is 2i right here. Or, I mean, yeah, we already know our lambda, it will be 2. So this is 2 right here. Then this is, okay, so this is 2, 2, 2 all the way. 2, 2, 2. Then in that case now, 2 minus 2. So everything just goes to 0. So all this is 0, 0, and this is also 0. Okay, so all this now is equal to 0, 0, 0 again. Yeah, from the look of things here, we just have okay, because we have 3 rows, write this column 3 times. So v1, v2, v3, v1, v2, v3, v1, v2, v, okay, lastly, v1, v2, v3. So you can put this over it, 0, 1, 0, so 0, 1, 0, next 0, 0, next 0, 0, 1, that is this now, 0, 0, 1, and last 0, 0, 0. So all this is equal to 0, 0, 0 in short. So next we just have, from here we have v2 is clearly 0. This v2 here, this is 0, 0. So v2 is 0 decisively. Then v3 is also 0 decisively. So v1 is missing. So we can just let v1 to be 1, right? So we just have v1, v2, v3 to be equal to 1, 0, 0. So we can say that uh so the eigenspace E2, right, actually spans the eigenspace, the span of that 1, 0, 0, basically. So eigenspace is just another a special way, I mean, writing your eigenvectors as a span, right? So you just say eigenspace to spans 1, 0, 0, basically. That's what happens there. So even if you don't understand this whole Z is zero, Y is zero kind of thing, but I mean, from what I've explained here, it goes without saying. I mean, if you just follow the procedure, you get the gist. Okay. Yeah, so you just get that the eigenspace is the span of 100. So let's talk about dimension of an eigenspace. So the dimension of an eigenspace is called the geometric multiplicity. So it's the dimension of an eigenspace they call the geometric multiplicity. So the geometric multiplicity of an eigenvalue is equal to the dimension of the eigenspace. Okay, so it counts the number of independent eigenvectors. So in our case now, because the lambda is 2, right? So the geometric multiplicity of 2 now is equal to the dimension of E2. So it counts the number of independent. In our case, in the case we just finished now, we had just one independent eigenvector because the multiplicity the of the eigenvalue is 3, right? So you have one eigenvalue appearing 3 times. So algebraic versus geometric multiplicity. Algebraic multiplicity so the number of times lambda appears in the characteristic polynomial. This is the algebraic multiplicity, while geometric multiplicity is the dimension of the eigenspace. And it is always that one is less than or equal to the geometric multiplicity of the characteristic of the eigenvalue, which is less than or equal to the arithmetic multiplicity of the eigenvalue. Then we have something about defective matrices. So we say that a matrix is defective if the geometric multiplicity is less than the arithmetic multiplicity. So then the matrix cannot be diagonalized in that case. Example, you have A is 2, 1, 0, 2. So of course you can see the eigenvalues will be the eigenvalue, there are two eigenvalues, 2, but they are repeated. So it's the same 2 all the way. So if you do a minus 2, 1, like you want to find vector, so you have 0, 1, 0, 0. So here, there's one free variable. So one of the variable is free here because it has no pivot. So in that case now, it means that you see that the geometric variable is just 1, which is less than 2. The 2 times this one is appearing. So you can say that the matrix is defective and it cannot be diagonalized, right? So then we talk about eigenspaces and diagonalization. A matrix is diagonalizable if the summation of all the GM lambda i's is equal to n, right? Like in this case, now where you got the eigenvalue to be 2. So if you sum it up, you get 2, right? Then in that case, you can have, but then the trouble is if they are distinct. So here now, if that was possible, right, that they are distinct, like it's not the same thing. So if like lambda I, when you have two, this doesn't work anymore. So but if it works, then you say that A is PDP inverse, where the columns of P are eigenvectors and D is a diagonal vector of eigenvalues. When we talk about the geometric interpretation, in 2 dimensions, eigenspaces are lines through the origin. In 3 dimensions, eigenspaces may be lines, planes, or the whole space, depending on if we have distinct vectors, we have the whole space. If you have only 2 distinct vectors, if all the 3 vectors in 3 dimension, if all the 3 vectors are distinct, we have the whole space. If only 2 are distinct, that is, only 2 are independent, we have planes, and then if only one is independent, we have lines. So they represent invariant directions like that. So imagine a diagonalization check here. So for the eigenvalues, you can see 4 and 4 appear twice. So lambda 1 is 4, lambda 2 is 2. So the arithmetic multiplicity of 4 is actually 2. That means it appears twice as eigenvalues. Then the arithmetic multiplicity of 2 is simply 1. If you add the two together, you have 3. So that goes like that. So talking about the eigenspace for lambda equals 4 now, that means if you do how we go about getting eigenvector. So a minus 4i will give you all this. So you have minus 2 down here. So in that case, you see that z is clearly 0, but others can be anything else, right? So because z is clearly 0, you have two free variables. So z is fixed, but these other variables you can take them freely. You can have x to be 1 and y is 0. You can have x to be 0 and y is 1, but z is fixed from what is here. And that's because this you are going to have minus 2z equals 0. So that means clearly z is automatically 0. So you have two free variables, x and y, because only the third column has a pivot. The first two don't have pivots. So those variables you can pick any free values you have for them randomly. So in that case, now we can say that E4, the span of E4 is 1 0 0 0 1 0. On the other hand, for lambda equals 2 now, if you try to do the span to you get 0 0 1. So you see 1 0 0 0 1 0 and 0 0 1. So if you do the diagonalization check, the geometric multiplicity, don't forget arithmetic multiplicity is talks about the number of eigenvalues, but the geometric multiplicity for 4 now you have 2, you have the dimension is 2 here, and for this one the dimension is 1. So as a result of that, if you add everything, you have 3. So since 3 is equal to n, then you can say that the matrix is diagonalizable. So despite the fact that the eigenvalues are repeated, but we are still able to find unique eigenvectors, independent eigenvectors, which make up the whole eigenspace. So it means that we can diagonalize this particular matrix 4 0 0 0 4 0 0 0 2. So in summary, we see that we see this key fact that the eigenspace of lambda is equal to the null space of A minus lambda I, and then eigenspaces are subspaces because they obey all the rules of zero vector, scalar multiplication, and of course addition. So dimension equals geometric multiplicity. Then they are also used for diagonalization and describe invariant directions. So we have practice problems for this now. So solve the following problems: find eigenvalues, eigenspaces, and determine diagonalizability when required. So the condition for diagonalizability, as we saw already here, is the fact that the geometric the geometric multiplicity of each eigenvalue, if you add them all together, if you can find distinct matrix eigenvectors like that, then you can talk about you can talk about diagonalizability, as you can see there. So try your hands on these questions, find the eigenspaces of this, then 4 to 6 now. You can try your hands on this too. So I want to try this too. Then 7 to 9, you have all this, and 10. Okay, so you want to try your hands. This is 8 to 10 now. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed already, I must thank you so much for doing that. If you haven't subscribed, I wonder why. Why not just go ahead right now and subscribe? And as well, you hit the notification bell so you can always get alerted each time a new video is released. Having done that, you may also want to become a member of this channel by clicking on join. That gives you some special privileges, like you get to see some videos first, or you see some videos exclusively without non-members seeing them, and we can hang out. I can consult for you on something in any area. I can help you as far as you're a member of the channel. Depending on your level of membership, by the way, you can have PDF copies of some of my notes based on your request. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.